Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts. I'm delighted to welcome Paul Bauman back to the Water Resources Podcast. Paul is a principal geophysicist at BGC Engineering in Calgary, and he recently returned from a trip in Chad where he was working on groundwater exploration using geophysics for the refugee camps and to deal with the situation there. So today, I think we're going to talk about his recent trip and the various refugee camps he worked at and many of the issues, the difficulties of exploring for groundwater, and then his recommendations to improve that situation. Thank you so much, Paul, for joining me. So maybe you can describe, how you got going on this trip and what led to it, UNHCR inviting you and that sort of thing.
Yeah, thanks, Bridget. It's great to be chatting with you again here. I work for BGC Engineering. We're an 800-person geoscience company. We have a foundation that specifically is focused on the company and using our professional knowledge to address whatever humanitarian crises, geohazards, water exploration, whatever's a good fit with our skill set. And so we had a little time, we had a little money, and we were looking for a good crisis to jump into. I contacted a number of organizations, UNICEF, UNHCR, various NGOs. And Ellen Milne from UNHCR responded. She's the global groundwater and geophysics lead for UNHCR out of Switzerland. And she directed us to the group there that was specifically looking at the Sudan crisis. That is the civil war and the 10 million people that have been displaced in Sudan, including the 2 million refugees that have come out of Sudan. And indeed, it is a crisis, probably the humanitarian crisis of our times, given the harsh conditions and the ongoing war and the magnitude of the number of people. And of specific concern to Ellen and that group was water. There's been about 1.2 million Sudanese refugees coming out of Sudan into Chad. And specifically, they're coming out of Darfur, West Darfur, where there's very clear ethnic cleansing and genocide occurring. And over the last year, there's been, since April 15th, new civil war, there's been 600,000 more refugees coming into Chad. And that part of Darfur and eastern Chad is essentially desert. There's very little water. There's no surface water. The camps that already existed there from the 2003-2005 Darfur Civil War already were lacking enough water, and then combined with the influx of another 600,000 refugees and another 400,000 refugees that they're expecting before the end of the year, these camps were desperate for water. The timing was quite critical. We certainly heard loud and clear that the best time to come to this area, the best time to work is January, when the temperatures are in the 20s. But by July and mid-July, end of July, you get very severe rains that make travel impossible. And the crisis is now. So we agreed to go in June, which in fact is the hottest time of year, and temperatures are in the 40s. So that's really how it progressed. Very, very informally, we contacted UNHCR. They identified the need. They had specific water concerns. They asked if we'd come right away, and we did.
And UNHCR, the UN High Commission for Refugees, they manage all the refugee camps globally, correct?
Yeah, that's right. I mean, worldwide, I guess there's over 100 million displaced persons, but one of the defining factors of refugees are those that are forced to leave their country, and really worldwide, and certainly in East Africa, but other places like Bangladesh, for instance, UNHCR is largely managing these camps and all aspects of management. So not just water, of course, which is of critical need, but food, security, education, and medical needs. So right now there's 19 camps on eastern Chad, very close to the border with West Darfur. A 20th camp is being constructed. Each of those camps is expected to grow out to about 50,000 refugees, so over 1 million refugees, and UNHCR is managing all of those camps.
And as you mentioned, Paul, this builds on the 2003-2005 war in Darfur. And so some of these refugees camps were existing and I guess are some new since 2023, since last April.
That's right. There's most recently 3 new camps, and then a fourth camp, a fourth brand new camp is being constructed right now. This total of 20 camps. Many of those camps, at least portions of the camps, you likely would not recognize them as refugee camps. So, for instance, the camps in the northern province where we worked, Wadi Fira, where they have very severe lack of water. The 3 camps we worked in, Tulum, Amnabak, and Eridimi, the volume of water that each refugee is getting ranges between 4.5 and 5.5 liters per person per day. So there simply is not enough water yet to significantly expand some of those camps. So the people in those camps are largely refugees that came from the 2003 to 2005 camps. And you see a lot of mud construction and narrow alleyways and thatched roofs. The camps look, to some degree, they look like villages that you'd see elsewhere in Darfur and in eastern Chad. But then in the expanded portions of the camps, and certainly in the new camps, what the UN does, they come in and they literally bulldoze the area. Everything's removed, trees, vegetation, and they put these sometimes prefab, often constructed on site, these small structures, essentially thin wood framing with tin roofs wrapped in plastic, and they're evenly spaced, and they put them there by the thousands. From the air, they look like Lego blocks. So the new portions of these camps are completely unmistakable. And so, for instance, south of Wadi Fira, the other province where we were working in Wadai, one of the camps we worked in was Dugi, and that's a brand new camp. It's only been functioning really for a few weeks, and it's just, as far as the eye can see, it's endless rows and endless alleyways, between which you have these essentially Lego blocks of plastic wood framing and tin roofs without a tree or a piece of shade in sight.
And the refugee camps that were formed in response to 2003-2005 war situation, many of the people that moved into the camps at that time are likely still there over this entire time. I mean, sometimes people live in these camps for a long time, it seems.
Yeah, that's right. And most people in the world don't realize that. They think these refugee camps are temporary, which they should be. I mean, the intention of UNHCR is either to repatriate these people to their home country, to get them third country repatriation. That is, they go to the States, they go to Canada, they go to Europe, or Rwanda, or some other place, or they receive citizenship or permanent residency in the country that's hosting them. But that's not the reality. I remember a statistic from the Kakuma refugee camp, where I've done 5 projects there, and the average time a refugee lives in that camp is 18.7 years. So essentially, many people born, live, and die in those camps, and they certainly live a significant piece of their life. And I believe in refugee camps worldwide. It's in UNHCR, and we're largely talking in East Africa. I think 17 or 18 years is an average.
It boggles your mind, doesn't it? For people to live that long in a camp when it's supposed to be a temporary situation, but it doesn't end up being. So you mentioned in Chad then where you were, that it's a semi-arid region and there's almost no water. There's groundwater, and that was your job then, was to try to find groundwater and use geophysics tools to help with that. And I like the analogy you used in the radio show that I listened to on CBS. With the medical imagery and stuff that we're so accustomed to these days, radiography and other things, and trying to see beneath the surface and see what the subsurface looks like and where you might likely find groundwater. Maybe you can describe that process a little bit.
Yeah, there's not, so this area, and again, we're talking eastern Chad and the border of Darfur. As you move further south in Chad, you get increasing rain. As you move further north, of course you're into the Sahara. I mean, we're real desert. We're working in what you'd call the Sahel, which in Arabic literally means the coast. And there's no coast for maybe 1,000 kilometers. Probably Lake Chad is the nearest coast of anything, and that's well over 1,000 kilometers from where we are. But I think the term Sahel, it comes from the idea not that you're on the edge of the ocean, but you're on the edge of the Sahara. So I think nominally you'd call this semi-arid, and rainfalls, again, nominally they're between, I believe, 300 millimeters in the northern part of our area and 600 millimeters in the south. But I would call it desert. I mean, in 3 weeks there, no exaggeration, I did not see one single blade of grass. And I think when rain comes, it actually can be quite sporadic, spatially. So some areas, some years might receive more and some less. And then the last few years, of course, all of Chad, related to El Nino effect and quite possibly global warming, has received less water than usual. But regardless, there simply is no surface water. So really your only source of water is groundwater. Chad does have varied geology, but here in the east, we're almost complete. The area is completely underlain by crystalline basement, largely from the geological maps and from what we could see, largely granitic rock. Having said that, there's not much hint in vast areas. There's not much hint of what's under the surface because the bedrock's covered by wadi fill materials, sands, gravels, clays, or a lot of windblown sand. I mean, we're constantly seeing Aeolian deposits built in real time. Every day we had a dust storm or a sandstorm. So definitely we're looking for groundwater, and fairly simply, our main target were these thick weathered crystalline basement aquifers that are known to exist in eastern Chad. I mean, more broadly across the crystalline basement aquifers of sub-Saharan Africa, which is about 40% of Africa, but certainly in these crystalline basement areas in eastern Chad. And what I had read is that because of I don't know if anyone knows precisely why, but because of the tectonic stability, where Chad has sort of been shuffled around over the last many tens of millions of years with plate tectonics and heat and temperatures and precipitation, the weathered zones in Chad seem anomalously deep. But it's these deep weathered zones in particular that we're looking for, the saprolite rock above the crystalline basement. So going from top to bottom, there's usually a cover that could be lateritic deposits. These red clays that characterize most of Africa, or windblown deposits or wadi deposits, and then beneath that and those could be a few meters thick, a few tens of meters thick. beneath that, you have these unsaturated saprolite deposits, these unsaturated weathered crystalline rock, and then hopefully saturated crystalline rock, and then hopefully below that a few meters or even potentially a few tens of meters of fractured rock, and then you're into fractured but unweathered rock, and then you're into the massive unweathered, unfractured crystalline basement.
And in your recording, the radio show, CBS radio show, you mentioned there were a few basic criteria that you use for finding good targets for wells. Could you describe those, Paul?
Yeah. So these camps are very far apart. Not necessarily so far apart on the map, maybe 20, 30 kilometers, but I'd say the roads are bad, but basically there's no roads. We're traveling cross country. And so it can take hours to get between camps. And then of course as in almost all countries that accept refugees, where are these camps? They're generally where the government, as well as the local tribes, and there's many tribal communities in Chad with their own different languages and culture and economies, largely pastoralist, nomad, semi-nomadic, and they have various ownership rights in the land. So essentially, you build your camp where you're allowed to build it. You don't cherry pick where the best water resources are, where there's already water wells, where there's potentially good grazing. You take what you get. So essentially, we come to the camp and we're faced with a vast chunk of desert, and where do you begin? And we try to break it down to three main criteria. First, of course, you have to be within a certain distance of the camp, a certain proximity, because you can only pump the water so far, economically. And then secondly, of course, you want whatever pumping and piping you have, you want to try to avoid crossing the major wadis where you're going, where typically in the rainy season you will get these flash floods that will rip out any piping, and this piping could potentially be repaired. They don't, of course, have frost or but so they're often above ground. But nevertheless, once that piping is ripped out, people don't have water. And then thirdly, so you need proximity to camp. Secondly, you need these thick weathered zones, and that's what we're looking for geophysically. And then thirdly, even when you find these thick weathered zones, it's not necessarily certain that they're actually saturated with water. And even if they're saturated with water and then they're pumped out, it's not necessarily certain that they're recharged. So you want to be in close proximity, not necessarily in these wadis, but in close proximity to these wadis, which of course wadi is it's commonly used geological term too, but a geographic term, but that's the Arabic for these ephemeral rivers that exist all over North Africa, but certainly in Chad. And these wadis can be very large. They can be a few tens of meters across, but they can be many hundreds or even a meters or even a kilometer across. And in eastern Chad, some of these wadis may drain from as far away as Sudan, and some of the larger wadis are known to flood every year. It might be for a few weeks, it might be for a few days, it might even be for a few hours, but certainly what we've seen elsewhere in similar environments is that with a good connection of granular material to the wadi and then into connecting to the underlying saprolite, even a day or two of flooding is enough to recharge these aquifers.
Yeah, that's amazing. So these crystalline basement aquifers, cover maybe 40% of the African continent, so they're quite widespread. And I think you mentioned that they're similar to the crystalline basement, the Shield in Canada, right? So it's been stable for a long time. So they've been allowed to weather, and then you develop the aquifer, which are made of these weathered material. And so are you usually able to get water in the weathered saprolite, or do you sometimes go down into the fractured basement and get water from the fractures, or is it mostly in the weathered? And the weathered zone, you said, can be like 30 to 100 meters thick.
Yeah, the weathered zones, maybe not the weathered zone itself. It can certainly be 100 meters to massive rock, but these weathered zones, for instance, Uganda, where I've worked considerably, typically the weathered zones are 20 to 30 meters thick, and here they can certainly be 50, 60, 70 meters thick. And yes, typically we're looking for the water in these thick weathered zones, and especially in this scenario for these camps. Why? Because these camps, big camps, they're going to be 50,000 people. They're in the desert. People need a lot of water. Typically, UNHCR targets 20 liters per person per day. And of course, even without the camps, the people in Eastern Chad, they're living there. They're digging wells. They're finding water in these shallow, 20-meter deep hand dug wells that they'll bucket out water, or they might even dig a 2 or 3 diameter hand dug well and bring a pump down there and pump out the water. But that's not enough water it's enough water for a few gardens, a few families, maybe a small village, but it's not enough water for a refugee camp. They need a lot of water. They need multiple wells producing 5 to 10 to maybe even 15 cubic meters per hour. So typically these fractured zones, from our experience and the literature, these fractured zones, it's great to drill into these fractured zones because you get good hydraulic conductivities out of these fractures, and it's good to screen across these fractures. But where most of the storage is in these saprolite zones, in these weathered zones, and of course the thicker the weathered zone, the longer the screen lengths you can run, the greater the yields you can pump, and the more likely a well will last through the dry season and maybe through a drought. So we're definitely targeting not just the weathered zones, but the thickest and deepest portions of these weathered zones and the most extensive portions of these weathered zones, and also weathered zones that well, as far as we can tell, geophysically, connected to either connected directly to the wadis, to these wadis that flash flood, or can actually be incorporated into these flooding episodes. And if that's the case, then we're also looking for areas where you have thick weathered zones, and then the cover material, that overlying sediment, is preferably sands, gravel, something permeable versus clays, which can also be quite common, since clays are one of the end member of these extensive crystalline basement weathering areas.
Right. So you mentioned, rainfall 300 to 600 millimeters a year, and then episodic recharge. Maybe you don't get it every year. Maybe the wadis don't flood every year. Or maybe it might be tied to El Nino conditions or Indian Ocean dipole conditions or things like that. I know in the Horn of Africa, they had, about 5 or 6 rainy seasons that were dry, and famine early warning system projected that, and tried to avoid famine in that region. So it's really tough situation. And your role then is to use these geophysical tools then to try to find the suitable subsurface conditions that guarantee the highest guarantee for getting water and that having reliable access to water over the long term. Maybe you can describe the electrical resistivity approaches that you use, ERT, that sort of thing, and how that works out.
Yeah, I mean, ideally in this program, as what we originally laid out, ideally we had a pretty deluxe geophysical program plan. Initially, we were going to go for a scout, bring some small portable logging systems. There's a lot of dry holes there, as well as producing holes that everything's cased with PVC. We were going to log them with downhole induction conductivity tools and gamma ray, and come up with the physical properties and come up with a program, and then go there with maybe fixed frequency EM and 2D resistivity, and probably some seismic to differentiate the shallow resistors with a granular material or simply massive rock. So we had this very deluxe program plan, but then reality set in. I mean, they needed us immediately, and very limited what of course we had to transport all this equipment to Chad, which we've done before. I mean, we've taken 30-40 pieces of excess baggage on planes across the ocean, but the tricky part is then getting all that equipment from N'Djamena, the capital, to the east, and you're flying on these small, unharsh United Nations humanitarian air surface planes that have very limited cargo capacity, and sure, our geophysical equipment is important, but so isn't the food and the pumps and the fuel and all the other things that they're bringing across. And then we're flying from the northern area, from the Wadi Fira area to the Wadai area. So we really had to pare down and really focus on exactly what we needed and what would give us our best chance of success. So we went with 2D resistivity, electrical resistivity tomography, and we brought cabling. And we, even though this is pro bono, we treat this like any other project, and maybe even more so with in terms of how much equipment we bring, and we always bring backup of everything as well as backups of backups. And so yeah, we brought electronics and cabling to do 2D resistivity surveys, essentially giving us the ability to investigate down to about 130 meters. And not only is that pretty much the maximum you'd ever expect for any type of weathering environment, but the drill rigs operating that area, they really can't drill any deeper than 100 meters. So that was a very practical equipment choice. And yeah, we bring, I mean, just not to get too deep into the weeds in the geophysics, but typically we're using this combination of what we call a gradient array, which is a sort of a combination of Wenner and Schlumberger and gradient arrays. But the main feature of this is, I would say, is that the transmitting electrodes are on the outside, and we're using all combinations of receiving electrodes on the inside. And the main point of that is it's even in these highly resistive environments, dry granular material, thick sands, thick unsaturated zones. It's really the best approach for good quality, high signal to noise ratio versus if you look through a lot of the literature, essentially all the literature that I've seen from Chad, everyone is using these pole dipole, well, not dipole, pole surveys, which give you good depth of investigation, but generally it's much noisier data and lower quality data. So we brought the equipment we need to get the best quality resistivity data to 100+ meters depth.
I'm afraid my geophysics background is pretty limited. I think the only stuff I have done is EM induction and downhole EM. But I mean, it really is a powerful tool. It's just another set of eyes to see the surface. And if you're trying to drill without that, I mean, long ago people would use dowsing and other tools and things like that to try to find water wells. But I mean, this really is extremely helpful. And so mapping these transects then that you develop, you can see the thickness of the weathered zones, and you can figure out where the best locations are to drill. I mean, the resistivity is controlled by the texture of the material, the salinity of the water, and things like that. So you're trying to find fresh water in coarse material that is connected to the wadi that recharges.
Yeah, in that CBC interview, I kind of, even though on the other side of the planet, in a lot of ways, exploring for water in Chad, it's similar to exploring for water in the Prairie Province of Alberta, in that you really can't see much at surface. In the Prairie Provinces, of course, you can have quite complex geology, but everything is covered by these glacial debris, by these tills, and there's not many hints in remote sensing, and there's very few hints in the landscape what's happening in the subsurface. And of course, you have vegetation in Canada as well. And in Chad, there's not a lot of vegetation, and what outcrop you do have, you do get tremendous exposures, but a lot of these areas are covered by aeolian deposits, wind-blown sands, and silts and dust, and of course the wadi deposits. So really, I mean, if you go through the literature, everyone has ideas from remote sensing and satellite imagery and lineament analysis and all that, and we use that too. I mean, it's a place to begin, for sure. It's a place to begin, and there are some really prominent features, for instance, like dikes, and also very relevant to that. You do get a sense whether you're in mafic basement rock or felsic basement rock, which actually has some practical implications. Generally, the felsic rocks will weather into more granular materials versus the basic rocks will, for instance, like dolomites will weather into more fine-grained, lower hydraulic conductivity material. But back to your question, Bridget, I mean, specifically the electrical properties in the subsurface are pretty clear. The massive unweathered basement is many hundreds of ohm meters and often many thousands of ohm meters. And why is that? Well, there's no porosity, there's no weathering, there's no fracture, there's no water content. Very resistive to the flow of electric current. I mean, moving up towards surface, and you usually move into a zone of fractured rock, and that can be a few meters thick, and sometimes it can be a few tens of meters thick. And that's still usually quite resistive because, I mean, what I would call sap rock, you have fracturing, which gives you some porosity, and hopefully it's water saturated fracturing. But what is that porosity? It's 1%, 2%, 3%, maybe 5%. So it certainly lowers the resistivities, and now you're looking at resistivities of hundreds of ohm meters, maybe a couple hundred ohm meters to 300 or 400 ohm meters. And actually, the fractured geolayers are usually difficult to define because you're still in these relatively higher resistivities, and they're often very, very thin. But above the fractured rock layer, then you enter the weathered zones. And if we can't see it, and if it's not thick enough that we can see it, then it's not of particular interest. But the resistivities, the electrical properties of these weathered zones are very diagnostic. They're typically between 30 ohm meters and 150 ohm meters for saturated weathered rock. So they're very diagnostic, very clearly mapped. They're not ambiguous with really what's above or what's below. As you further move up in the section, the resistivities might drop further as you get into increasingly weathered rock that might weather into the end member of clays, and you might get resistivities of 10 to 20 ohm meters, or even less than 10 ohm meters. And of course, that's not a particular interest, and in fact can have negative implications if those superficial clay layers, if they exist, are impeding infiltration of water. Or as you move out of those weather zones, you can move back into layers of hundreds of ohm meters, essentially dry, granular materials that are either windblown or deposited by fluvial deposits. And those are, again, a good sign, because if they're connected to these flash flood features, you'll get infiltration through the overburden into these saprolite zones. You'll get recharge.
So at each camp, then you did a number of these surveys, electrical resistivity surveys, and it's nice that you have such a big contrast then between the basement and the fractured rock and the saprolite and the laterites and stuff like that, so that you can readily map the depth that's most appropriate that you think for drilling wells. So how many kilometers of transect do you think you covered at each of the camps, and then how many targets did you end up with for each of the camps? How many wells are you suggesting?
Yeah, at each camp, we collected between 1 and 2 kilometers of data, depending how many days we were at the camp. Actually, some of the camps we even collected up to 3 kilometers. We collected a total a bit over 15 kilometers of data. The other very important piece of information that I didn't mention in terms of where we sited the wells is, and we do this quite literally daily consultation with the UNHCR. We'd be speaking with them or texting them back in Geneva or elsewhere at their headquarters. The other criteria is we would try to tie at least one of our lines in with an existing well, whether it was a dry well or a good producing well. And for a couple of reasons. One is we have these geological assumptions and these ideas and these generalizations of what's there based on geological maps, based on satellite interpretation and these ideas of what the physical properties represent, but they're not certain. And there's nothing like tying into a good well with really good cuttings and a water level and a screen length and a yield, or into a well that was drilled into massive rock and produced nothing, but at least we know the geology. There's nothing like that to confirm our interpretation. So yeah, it certainly is helpful tying into these wells to give us confidence in our interpretation. And for the client, well, I actually really say the client is actually the refugees. Let's say UNHCR, to give them confidence in that what we're doing and the interpretations we're coming up with are meaningful. So yeah, we would collect say between 1 and 3 kilometers of data at each camp, and yes, at every camp we feel we got multiple targets. So that is, we would place our targets in relatively close proximity to large wadis, where proximity to the camps, certainly in places that are practicable enough that they can pump water. And it's hard to give an exact number, but I would say between 5 and 10% of each section showed very thick weather zones that we felt were highly prospective water well drilling targets. I mean, we're confident that we have some great targets. And I mean, another thing that gives us confidence too is that they were drilling wells without us. I mean, without good geophysics and sometimes without any geophysics. And they were drilling a lot of dry holes, but we're also having some successful wells. So I like to think that, well, with a bit of science and a bit of a good subsurface imaging. Of course, we should find a lot more prospective zones. And yeah, I mean, I did mention, too, we would like to tie in at least one line to at least one or two existing wells. Again, whether they were dry or wet, especially in case there's any surprises in the local geology. And sometimes there were surprises. I mean, one of the largest aquifers in the world, of course, is a Nubian aquifer, Nubian sandstone aquifer that extends across much of North Africa into the Middle East and does extend across much of Chad, but that's much further to the north. But nevertheless, where we were, there actually were outliers of Nubian sandstone. So real outliers, like giant, extensive blocks of Nubian sandstone, completely surrounded by and enclosed by a much older Precambrian basement. And so there were various geological surprises, these massive dikes crisscrossing sometimes basic dikes, sometimes felsic dikes, various features crisscrossing our exploration areas. So we have a model in our minds, but at the same time, we're trying to keep an open mind to the interpretations and the petrophysical interpretations wherever we went.
Right. And so it's great to have that to ground reference and to validate your assumptions when you do the geophysics approach. But your background in your work in Africa, I mean, I think you have found that using this imaging and stuff, that you can greatly increase the success rate of drilling good boreholes, good wells that produce it seems from your past experience in many of these different refugee camps, you've greatly increased the odds.
Yeah, no, I mean, I would say, geophysics is widely used now in Africa, but good geophysics is not widely used. And in 2022, 23, we did programs in the Kakuma area, actually not in the refugee camp, but in the Turkana hamlets surrounding Kakuma. We did a program in northern Uganda and a program in the most difficult district in southern Zambia, the Zimba district, and that's one district in 116 districts in a country the size of Norway and Germany combined. And yeah, I mean, the Zimba district, the success rate was between 1 in 10 and 1 in 20, and we had not perfect, but we were 6 for 16. And geophysics was, certainly geophysics was the main guidance for all the drilling there. And I would be very grateful if UNICEF and other NGOs working in Zambia right now, which is suffering from a tremendous drought and a cholera epidemic, all of Southern Africa is that they're getting the other end of El Nino, the El Nino effect from East Africa. That is, they're getting drought, and there's a lot of focus on improved sanitation and hygiene to combat cholera, but really what they need is more water. And so yeah, we definitely geophysical methods, and there we use time domain EM, fixed frequency EM, and a lot of resistivity were critical in the success we had in northern Uganda, where we have a lot of experience. Success rate there was 100%. And we've done enough data there, and there we have done a lot of borehole geophysics and surface EM, and we've done a lot of well repair where we log the wells. We know what a good aquifer looks like, so we essentially never drill a dry hole there. And then in the Kakuma area, which was suffering tremendously from drought and from the Horn of Africa drought and famine, and was desperate need for water, and in many at least social perspectives and the job perspectives, very similar situation to what's going on in Chad. There we sited 4 wells with 3 of those being successful, and without geophysics, I don't think we would have had any success there at all. So so yeah, geophysics I believe, groundwater is really the especially in rural areas in Africa where there simply is no access to surface water, and where groundwater has such an improvement on water quality over surface water source. It's essential to moving development in sub-Saharan Africa forward, and geophysics is really the only reliable method of identifying where to drill your water wells.
And so you've identified these targets now, and the drillers in those refugee camps or people in that community will drill those targets, and then you will stay in touch, I guess, as they develop those wells and stuff. Is that how it works?
Yeah, that's all happening now. So in the and I don't really fully understand the mechanics of it myself, but basically you can think of UNHCR as maybe it's not a great analogy, but they're kind of like an oil company. It's they run the camp. It's their responsibility. They have the big picture. They bring a lot of the money. But then who actually does the work? Then they have their what they call implementing partners. So those are usually NGOs, and a lot of them might be the sort of the bigger ones. You might have heard of Red Cross, Oxfam, Action contre la Femme, Med-Air, whatever. And they're the ones that are actually on the ground, MSF. They're the ones that are on the ground actually doing the work. And then all this work related to water, it all falls into what in humanitarian speak they call WASH. So water, sanitation, hygiene. And then these NGOs, they divide that up. So you'll have for instance, the sanitation, some NGO will take charge of sanitation, which, for instance, would largely consist of constructing pit latrines. And then another one might take charge of hygiene, which might largely consist of giving people the facilities and the knowledge how to, wash their hands, avoid bacterial cholera spreading. And then you'll have an NGO taking charge of the water part, which is, of course, what interests me in the WASH. And so one of these larger NGOs will take up the reins of drilling the wells, and that's happening now. We're in direct and essentially daily communication. We will be a while before we have reports, but we fully processed our data. We've fully given interpretations, and we'll provide these NGOs with everything they need to the best of our ability, the best of our interpretations of exactly where to drill and the expected depth. We would expect them to encounter these weathered zones, encounter water, encounter massive bedrock to make sure they don't waste their drilling resources. So that we'll give them Google Earth maps with pinpoint locations. We'll give them photogrammetric maps that we constructed from drone photogrammetry that have incredible high resolution. Like even without a GPS, you can guide someone to the precise location by looking at which tree or which hut or which boulder, referencing that. And of course, we'll give them GPS coordinates and the relevant UTMs as well as lat long. So we'll give them everything they need and a range over which they can, if they can't drill in one particular location because of whatever logistical reason, they'll have a range of sites and alternative sites that they can choose from. So we try to make it as turnkey and easy and surefire as possible for them to identify the proper location and drill to the proper depth.
And I know we're getting low on time now, but will these wells be mostly hand dug, and will they have a pump stand in them, or will they be piped water to the units, or what will the ultimate distribution be like?
Oh, these will all definitely be machine drilled. Again, they're looking at big production wells here, so
Okay.
minimum they won't produce anything that's yielding less than 5 cubic meters an hour, and ideally, 10 to 15 cubic meters an hour. So they'll all be machine drilled, cased. They'll all have downhole submersible pumps. They might be solar, but depending on how much water and the water needs and and how much they might want to pump. They might also be run off diesel generators so they can pump 24/7. And typically what happens, again, depending on the water needs, typically they'll drill the well, put a pump in, and then they'll immediately start, if they don't have piping, and they'll start trucking water to overhead tank systems in the camps, and while at the same time putting in the piping so they can reticulate to the camp, and then the reticulation, essentially the piping distributing through these camps, depending how much water, how much piping, how much refugees, the geography of the camp, but the piping will distribute it throughout. Well, the piping will go directly to these overhead tanks, so they're not dependent on power to distribute water, and then they'll use gravity to distribute to usually hundreds of tap stands distributed across the camp. So hopefully everybody within the camp has relatively easy access of few hundred, but hopefully even tens of meters to get to these various tap stands and access water. And then of course, maybe one of the most important features of these centralized distribution networks versus, for instance, hand dug wells or decentralized systems, that the water is always chlorinated. There's usually a drip chlorinator, usually drip chlorinator coming out of the well before it goes into the tank.
Well, that's fantastic. Yeah. And I'm really impressed that BGC Engineering has its own foundation and supports this work. And I know we're running out of time, but it's great that you guys are so nimble and able to respond to these crises, because it seems like an extremely important part. I mean, you said that the optimal time is to go in January, February, but you end up going in the midsummer when it's 40 degrees C there, or like over 100 Fahrenheit, and you live in Calgary. That must be pretty difficult. And so I really commend you and BGC Engineering for doing this. And are there any other points that you would like to make on this podcast, Paul, that you would like the listeners to hear?
Yeah. We all hear about these humanitarian crises, and certainly the needs are very great. There's many of these crises going on. The one in Sudan is, and I've worked in many refugee camps, and they're all crises, but most of them are, I guess what I'd say, chronic crises. They go on for decades. The situation in Sudan absolutely is acute. I mean, you have a couple million people being pushed into the desert. There's no water. The war is ongoing. They're lacking food. I mean, they're really lacking food, water, sanitation. And I mean, for instance, when I say lacking food, for 3 months, January, February, March, UNHCR did no food distribution. People got no food. It just wasn't enough money. And now the distribution, in at least some of the camps we were at, the distribution is actually in cash of 7,000 Central African francs per person per month, which is, I forget what that is. It's maybe like $12, $13. And with these food distribution, food prices go up. There's not great shopping in any of these areas to begin with. It's a critical situation. So I guess, an overall message would be, people should push their governments or support NGOs that are working in these areas, and I mean, not only are they trying to make the situation better, but really it's a struggle just to keep people alive. It really is that situation. And then I guess on the bigger picture, this dramatic refugee situation in East Chad that's been ongoing since the last Darfur War. It's of course coming out of the same crisis in Sudan, this civil war, and people should be. What brought an end to the 2003-2005 war was public outcry, and there is no public outcry on this civil war, but that's the only thing that's going to bring this this war to an end, because these opposing armies, the Sudan army as well as the Rapid Support Force, that's the opposition. They're, of course, where are the guns coming from? They're coming from Canada, the US, the UAE, England, other places in Europe, and Iran, and yeah, public outcry is what's going to bring a stop to the arms flow, and hopefully a stop to this war that right now has no end in sight.
Well, thank you so much for talking today, Paul, and thank you for doing all this great work, and to your colleagues also who went out there with you. And you have a presence in Facebook, and we will include highlights with the website with links to various things that related to your work. And so I really appreciate your time, and I hope you're enjoying some cooler weather where you are in your cabin at the moment.
Yeah, thank you, Bridget. I'm up in the mountains, and it's quite nice. And yeah, no, I appreciate your interest, and I mean, not only in our work, but also it gives some profile to this ongoing humanitarian crisis in Northern Africa.